Hey, students, I got a great question here from our chapter 13, some more. Actually, again, from the harder book. It is from volume 2, chapter 1 of the University Physics. It's number 54, and it has to do with thermal expansion as well as global warming. And so it was kind of a fun problem to do because we talk a lot about sea level risings. And what often gets discussed about it is the melting of glaciers. And so, like this one says, global warming will produce rising sea levels, partly due to melting ice and partly due to the expansion of water. And that's the part that doesn't get talked about much. It talks about more water because of the melting of land ice. Because, by the way, remember, melting of sea ice does not raise the water level. It's only the melting of land ice. But we don't often talk too much about the expansion of water, and it's kind of interesting because we are probably within the next 5-10 years, more of our sea level rise has to do with thermal expansion than it does actually have to do with water. And I wish the problem would have said that. It just says partially due. And it's true, it's partial in both cases, but it's a bigger percentage. Anyways, so the expansion of water is a bigger reason for our expansion than the actual melting of the water. And that's kind of interesting. But anyways, this problem emphasized that it's a little of both. And it goes on to talk about both. And in fact, I decided to kind of start this problem by printing up the graphs because this graph shows the Earth's temperature for the last 500 million years. And so we're right here. Here's the last 500,000 years. So this is in thousands of years. This is in millions of years. But you can see that in this area that we currently live right here, there's been a huge increase in our temperature. And so our sea levels have been rising. But what I really like is how this one in the last, 500,000 years, or even going back millions of years, shows how warm the Earth was. And a consequence of that, many times, here, this line, this is the one from NOAA, is the line showing where there's actually no ice. And so here is parts of our history, the Earth's history, particularly here during the dinosaurs, where we don't have any polar ice, and the water level is very, very, very high. And you see that, and we talk about that a lot. You don't see it too much where we live. I was about to say, when we hike in our mountains, you see a lot of marine fossils, shells. And although that's true, that's really more uplift. And so living on the coast of California, all of our land used to be underwater, and it is no longer underwater. But it's not because of ocean level changes. It's more of uplift of the land. But I was thinking further south in San Diego. San Diego's just loaded with mesas, and it's kind of fun to get to a high mountain, Mount Soledad, for example. They're in La Jolla, and if you look out on San Diego, you'll just see mesa after mesa after mesa, and these are all wave cuts. These are all places where the water level, and you could just stand there and look and say, okay, well, at one point the ocean level was at that spot, and then that spot, and then that spot, and you could see where it had come up and cut and leveled the water. Or maybe a better example here in the United States is the middle part of our country. We get lots of oil in that Permian Valley, which is West Texas and eastern New Mexico, heading north even into Oklahoma. Oh, and then way north up in Canada. But that was all an inland sea. And so back here, during these time frames, the water level is so high, that was just a giant shallow sea. And all that biomass sank to the ground and now has become oil and shell. And anyways, I diverse quite a bit here. But again, let's go back to this because our sea level is rising because of the temperature change. It'll be interesting to see what happens in the future. Does it follow one of these patterns that we see for the last thousands of years, or does it continue to rise given all of our burning of fossil fuels? So let's finally jump back to the problem and show how much actually it expands by just based upon temperature. So it says global warming will produce rising sea levels partially due to the melting of the ice caps and partially due to the expansion of water. Okay? To get an idea of the size of this effect, calculate the change in length of a column of water. So I'm going to pretend that I have this long column of water that is 1 kilometer high. For a temperature increase of 1 degrees Celsius. Assume the column is not free to expand sideways, which of course makes reasonable sense. You would have a bunch of columns making up the ocean, and they can't really expand sideways because eventually you hit the landmass. And so here is the coastline on the two sides of the ocean or the sea. And so as the water level rises, it can't really expand out. Although I guess it could, flood a little bit. But that's kind of minor. And I think they go on to kind of explain that. What do they say? Only parts of the ocean very close to the surface can expand sideways into the land, and only to a limited degree. As another approximation, neglect the fact that the ocean warming is not uniform. Oh yeah, so we're just going to say the whole thing warms 1 degree to give us some kind of idea. So like I said, it's really kind of a fun problem, and I like it because it really points to the rising sea levels connected in a greater sense to the expansion of water than to the melting of ice. Well, this problem doesn't show that ratio, but it does show how big this one is. So let's go delta L. Oh, sorry. Let me go delta V then is equal to beta times the initial volume times the delta T. And so this whole column of water is going to expand in volume. But here's the interesting and neat thing about a fluid is when its volume expands, its width and depth cannot expand. And so all the expansion gets pushed to an increase in height. And that's why you'll have liquids, that kind of appear to expand a lot more in a kind of a thermal length expansion than like your metals. In fact, I went ahead and printed the chart from your book because, as you'll see, here is how much they expand linearly, and here's how much they expand in volume. And as we were supposed to show in problem number 60, these are mathematically connected, but for your solids, they expand in their length, their width, and their depth, which gives them a volume expansion. But when you get down here to the liquids don't really have a set length or width or height, so they only expand in their volume. And so something like a mercury thermometer you build by putting mercury down in the bulb. And when you warm up the mercury, it expands and goes up the capillary tube and giving you higher marks along it. And that's what we're going to see here. Again, that's why the expansion of the sea level can be surprisingly more than you realize just from the temperature change. because all of what would have gone into the expansion of its width or its depth gets squeezed, and because it's a fluid, it can flow that way, and it will go up. And so that's why we like our thermometers made out of things like isopropyl alcohol, or even an old-fashioned thermometer made out of mercury, because it's a liquid. That's the key. Especially since when you're warming up the thermometer, the glass actually warms up, and it too would grow. And so if they just grew the same height up, the liquid and the glass, you wouldn't see a difference, and you couldn't use it to measure the temperature change. They would just grow the same amount. But it doesn't work that way. Fluids are just that. They flow. All right, but let's actually do this problem, because it's not really a very long problem, not nearly as long as the 11 minutes I've been talking about it. So if I were to think about this problem and say it's new volume, I would say, thinking of it as a column, it would be its original cross-sectional area times its new, I'll call it length. Actually, since I'm going up and down, let me call it height final. Oh, I'm sorry, this is a change. Let me try that again. Delta V might be its final volume minus its initial. And I would think about this as a column that has some kind of cross-sectional area A and some final height, minus that cross-sectional area times its initial height. And so this is my delta H. I'll factor out the cross-sectional area and have a delta H. So this equation, the delta V equals beta V initial delta T, would look like this. This side would be cross-sectional area times the change in height, whereas over here, this is the initial height and the initial cross-sectional area, okay? And notice then the cross-sectional areas cancel off, and I can get a formula that will help me answer this question, which is, what is the change in height? And so it's the volume expansion for water. So let me come back to the little chart here that's been measured. Here's my liquids going down. It looks like water is right there. So 210 times 10 to the minus 6. My initial height from the problem says, imagine this being 1 kilometer, which I'm going to write as 1,000 meters in length. And then my change in temperature is a 1. And they gave me some nice even numbers that I could then simply put the 1,000 together with 10 to the minus 6, and then I could be left with 10 to the minus 3, which would then go 0.21 meters, or, interesting, 21 centimeters. And that's quite a bit. And that was the whole thing I've been saying since the beginning. Warming up 1 degree Celsius is going to give me about 21, and this little tiny ruler is not quite 21. I thought it was 20, but it's, a little bit more than that. And so that's the warming just of 1 degree. And I would also point out that's also for only 1 kilometer of depth, where 1 kilometer, and I guess that's 5,000, 60% of a mile, 5,280. Yeah, I think the average ocean depth might be about twice that. So if we wanted to do this with a little more accuracy, I think we'd have to double its length. But I'm not sure what the average ocean depth is. I know some places it's, Mariana Trench, it's 7 miles or some ridiculous thing. But anyways, all right, that's the problem for now. All right, take care.